Welcome to the National Museum of the United States Navy. I'm David Barker, an educator here. The area that the Trieste dove is known as Challenger Deep, the deepest known point of the ocean. You can see it on the map. With your instructor's help, first locate the Western Pacific, then southern end of the Marianas Trench, near the Marianas Islands. Before we get into the Trieste and its deep dive, let's compare it to other submarines. A submarine can dive, but not as deep as the Trieste. It has a skin which is twofold with water sleeve between them. These look very much like the BCD or lifting body of the Trieste, so they can move through the water with ease. A BCD is a buoyancy control device as seen on divers. Their proportion is its BCD or tank, with separate chambers as noted on the lines on them. The Trieste can be taken apart and put back together, which makes it ship a lot easier. In other words, the top balloon-looking section is one major piece and the sphere is the other. Where a sub and a diver use air to adjust the buoyancy, the Trieste uses aviation gasoline to lift it from the depths. On the buoyancy section, there are two tanks of steel shot, ball bearings, that will pull the craft down to the bottom of the ocean. They can be released either by timer or manually. A normal sub just uses compressed air blowing the water out of its sleeve. Time for science. We know that divers and subs use air and water displacement to rise and sink, while the Trieste uses aviation gasoline and steel shot instead. Boyle's Law. Simple rules. PV equals C. Pressure, volume, constant. Don't despair. Air is pushed out by the water or pressure. How much water is the volume? Or in Trieste's case, the tank full of aviation gas represents constant. As you dive in the ocean, pressure goes up, doubling. 33 feet equals 1 atmosphere. Every 33 feet, the pressure doubles. 66 feet, it doubles again. Now, when you're talking about Boyle's Law, the biggest thing you have to look at is the change in pressure. So, the device that we see in here, when we add pressure, something's going to happen to it. Add pressure, and it's going to go down. What happens is the air inside of the pipette, which is the device inside, it still has the same amount of air, but the volume of the air has altered. It's became tighter. Now when we release the pressure, it's changing. Basically, as we add pressure, it takes up less space and it goes down. When we release the pressure, it's still the same air, it just now is increasing its space and it's able to come up. That is the basis of Boyle's Law. Boyle's Law you have to follow as you dive. You don't want to have the problems that others do. Again, pressure, it goes down. Release pressure, it'll come up. Now, we'll explain that a little more when we're talking about the Trieste, which is still using Boyle's Law, but in a slightly different format. Where a regular submarine skin is rather thin compared to Trieste sphere, the sphere being 5 inches or 12.7 centimeters, it's a little thicker. With the side view, we see the segment and the ladder section to climb into the sphere. Climb into the sphere where pressure is held at bay, as opposed to the thin skin of many other crafts. Thinner skin crafts at too great a depth will crush, as seen here. The loss of the Thresher in 1963 is one sad event due to Boyle's Law in crushing action. The Thresher sank in 8,400 feet of water. Now let's get back to the Trieste. The Trieste is lifted and lowered into the sea. We can't talk about the Trieste without a quick explanation of its dive and some other facts. Just imagine how cramped the sphere is. 2 men, all their gear. Now you're going to climb down from the sea into the sphere. The descent to the ocean floor took 4 hours, 47 minutes. With limited lighting, you're only able to see what is just outside of the sphere. They spent 20 minutes on the floor of the ocean, with a temperature in the cabin of 45 degrees Fahrenheit. The ascent took 3 hours and 15 minutes. Thanks to Trieste, other craft have been developed. DSV Alvin, for one, June 5th, 1964 it was launched. Though its sphere has been changed, it is still going. The DSRV system, of which they have made a number so far, started January 24th, 1970. Thankfully, Don Walsh was able to come for the 60th anniversary, January 23rd, 2020. I had the great pleasure of meeting him here.
Hello, and welcome to the National Museum of the United States Navy. My name is Mike. We're going to talk about radio detection and ranging, or as you better know it, radar. So let's start with what happened before radar. How does a Navy vessel see a hazard upcoming on the horizon? Just as I described, they see it, they look for it, it's line of sight. There are going to be sailors up in the rigging in the age of sail or in some high point in later eras who are going to be watching through telescopes, binoculars, other optics to see if there's some sort of storm coming, the enemy is coming, or whatever else. There's also going to be at some point aircraft that can be sent off to check out and a little bit further ahead of the vessels. However, there's no great long distance answer yet. This is going to come much later. This is going to come in the 20th century, and it's going to come in the form of radar. It's going to be very advantageous because if you think about it, if you can only run away from or react to stuff that's within sight, it's much closer to you, isn't it? So if it's that much closer to you and it's a much stronger, faster vessel, what are you going to do? You're going to have that much less time to save your crew, to save your sailors in one way or another, whether it be by standing and fighting or by withdrawing, beating a hasty retreat and fighting again another day. By the late 19th century, we're starting to experiment more and more with radio waves. So radio waves are going to be sent out, and various European nations are going to realize various different possibilities for these radio waves. The United States is not going to be that far behind, and frankly, most nations are going to start seriously researching radar itself around the 1930s. And in the 1930s, the U.S. Naval Research Laboratory right here in Washington, D.C. is going to start experimenting with their own sorts of radio. And actually you can see a remnant of this behind me. This is an XAF radar receiver right here that's going to be one of the earlier developed by the Naval Research Laboratory. So how does a radar exactly work? What are they doing? Well, like I said, this is just the receiver. So this is just kind of where the sailors, the technicians, are going to be controlling the actual device itself. So there's going to be a transmitting antenna, which is going to send out signals that are going to bounce off, essentially. It's these energy waves that are going to bounce off distant objects. And it's going to kind of diffract. It's going to scatter in various directions, but the most important ones are those that are going to come back to the receiver. There's going to be an antenna, receiver antenna that is going to take in these signals and bring them back to the receiver set here, where a sailor is going to be waiting to interpret what exactly is going on around them. It's going to give the Navy sight beyond the sight line. And that's going to give precious moments which you can use in order to keep your sailors safer, conduct maneuvers more successfully. So we have a little kind of a demonstration set up for you that we can go ahead and start on. What you're essentially going to need is a ball or a ping pong ball, so like rubber ball or a ping pong ball, something small, a couple of objects that you can set up, and if you want to create a nice launcher, some paper, tape, and a rubber band. So welcome to the Museum Education Center. This is where on STEAM Saturdays, when we're able to welcome you back, we'll have most of our activities and experiments as needed. So keep an eye on our website to see exactly where you go. But here I've got a little bit of a demonstration set up for you in which we're going to take these rubber bouncy balls here, and these are going to act as your radio waves that are being sent out and that are going to deflect back to you. Over here we've got a couple of objects. These are just plain old tubs that we have in storage here for education supplies. This larger one can be something like an enemy ship or something. The smaller one over here, it could be something like an aircraft formation, something else of that sort. Just pretend whatever you want to. In the end, most importantly, what they are is an object to be detected. So, in this case, I'm just going to use my hands. Some of you might get creative, make kind of a launcher for it, whatever else. So if you have a launcher, that's going to be your transmitting antenna. With me, it's going to be my hand, just so I can have a little bit more control over where it's going. If you want to get really fancy with it, you can actually set out angles. You can just go ahead and label angles at which, and you can try to determine what angles that ball is coming back to you from, things like that. But for the purposes of this, we're just getting a basic visual here. So what I'm going to do is I'm going to go ahead and I'm going to roll a ball towards this, and there we go. It came back to me. And when it came back to me, that just tells me that there's an object right there, as opposed to right here. It didn't necessarily come back. Sometimes also it'll actually deflect in various directions, and so you'll have various difficulties when it comes to that sort of thing. But also you can hit it off a different angle, and you'll be able to tell a little bit more about the size of the object. Going at the more distant one, you'll see that it actually takes the ball a little bit longer to come back. And especially if you use a mechanical device and you see a lot of the same amount of pressure, of energy moving out, then you'll see some of these take a little bit longer than others. Mine, I've been doing a little bit of variable speed, so it's a little bit harder to tell. Regardless, this is what gives you a little bit of a visual there of what you're looking for. A radar signal is going to move out. It's going to strike the object. It's going to come back again. And then from there, you are the receiver. You are calculating the data on what you might be seeing. So there are probably going to be a lot more elaborate experiments that are out on the internet. I do suggest you go ahead and take a look at those as well, as you should never be done researching, you should never be done exploring. And so you can do all sorts of neat activity, ranging from more sophisticated versions of the same piece to actually having like microchip sets and making your own kind of electronic radar system. So keep it up, keep experimenting, and enjoy. Now that we have seen a visual on how radar works, and we've seen a large set that you would have seen on a large battleship or aircraft carrier, what are we going to use when it comes to aircraft? Aircraft are gaining prominence during the Second World War. They have a larger distance. They are able to be used as forward observation. So we're going to have to develop smaller sets, such as the one over here, the ASB, the most common of these sets among the most common of these sets, with kind of a piece sort of like this one underneath the wing that are going to send out signals. And they're going to be able to detect battleships at around 40 miles or so, and they're going to be able to detect submarines at around 5 or so miles. Aircraft similar to the Catalina over here, the Ventura or the Liberator, all of these are going to be various aircraft that the U.S. Navy are going to be used to kind of get eyes out, further out, so that we can get more and more warning. Because as we mentioned before, every second counts when it comes to saving sailors' lives and turning the tide of a battle. So developing these smaller systems will allow us to find these various different dangers further ahead of time. Also, another danger we haven't talked as much about, because we've talked about what you can't see over the horizon. How about what we can't really see under the sea? Starting in the First World War, you start seeing in the introduction and evolution of submarine warfare. That's going to be continuing through World War II, especially in the Atlantic, although also in the Pacific, certainly. And so finding these undersea threats before they could get within the picket line, within the formation of a carrier group, is a very important task, as a submarine hitting an aircraft carrier could be very devastating. So we send out these aircraft ahead of time with this radar. We find these submarines, and then you can send forth your destroyers, aircraft with death bombs, or other submarines to help take care of that threat ahead of time. All right, so here at the National Museum of the United States Navy, we have a lot of great dioramas as well as artifacts and other pieces you should check out. One that we often see missed is right here in this very section. So this is a little bit of how radar would kind of work from an aircraft. So you see the aircraft up in the far right-hand, upper right-hand corner there. He's going to send out signals down towards this submarine there, revealing its place as the submarine is now bouncing back those sound waves as we've talked before. So this is basically how anti-submarine operations could work, in which the aircraft goes towards a suspected area and the radar begins to work. After that point, they're going to go ahead and call in whatever forces are needed to take care of the threat. All right, so here we are in the Pacific section at the National Museum of the United States Navy, and you might be noticing some gloves right now. Whenever you handle artifacts, you have to do so safely. Finger oils can help corrode these artifacts, so whenever you're here, please be sure not to touch without museum staff and gloves present. That said, right here we've got an amazing piece that I can't help but touch with these gloves, safely with these gloves. This right here is a Model SQ radar. We talked about air, we talked about sea. How about land radar? This is a more portable unit that can be used to help set up in the islands that the U.S. forces are bouncing around in the Pacific theater. And by setting up these in various sections, hazards and dangers, or at least predict them a little bit more accurately. So right here you can see the antenna control unit as it spins around as you're searching for those signals to send out and back. And one thing we're searching for is going to be, and especially late in the war, suicide bombers, kamikazes, as well as the Oka bomb. We have one here in the museum, a training model of those, so definitely come in and see that. But during the Battle of Okinawa in 1945, as the war is about to end, there's going to be a web, a whole net of these radar stations set up around the islands there to help predict where these suicide bombers are heading towards. It's going to save many lives of sailors, Marines, and soldiers on ships around the vicinity, because a devastating hit from one of those Oka bombs really could do a lot of human and physical damage to the vessel. So these are going to be life-saving measures right there. Being able to predict that is extremely important. So we've talked a little bit about technology. How about the people behind the technology? Because the U.S. Navy has a great deal of technology that you can really focus on, but without the human element, it's not going to work. And so one of the initial rates that's going to occur is radarmen. Radarmen is going to be the initial specialists who are going to go to special U.S. Navy schools and figure out how to learn this new technology during the Second World War. And they're going to become vital parts of the Navy team. These individuals are going to have to stare at screens all day. They're going to have to be able to help repair, although there are also other mates that are going to be able to help with that aspect of it. But they are going to have a great deal of influence on the decisions made by higher commanders. So these enlisted individuals, and we often think about officers in the military, these enlisted individuals are extremely highly trained, as well as they are, the radar man is going to be essentially the rate through World War II into the 1970s, when they're going to become operations specialists who have a much wider variety of tasks and jobs. So I definitely suggest that you go ahead to Navy.mil or somewhere else like that and find out more of what some of these individuals do. But it's quite the far sight from individuals who are going to be standing somewhere high and staring through a glass, which does take its own seasoned eye. It's all about the training, and so you're going to be trained in different ways for this. Radar technicians does not mean you are getting rid of individuals with optics. Right here we have one itself that you are still going to need to see at a distance with and help to identify. Here at the museum we have an amazing collection, and certainly if you go to the Homefront exhibit, you'll see a little bit more about the training these individuals go through. Just to be able to do some of this, you'll see in that exhibit anything ranging from ship models to help you identify by sight what type of ship, or even in some cases what specific ship that you are seeing at a distance. Also, we've got records, and still a somewhat new technology. I mean, it certainly had been around since the early 20th century, but that's going to be used to help record training, just as we sometimes see podcasts or MP3s or something like that today. As we move beyond World War II, we start to see different uses of radar coming out. One of which is going to be with the National Weather Service. It's going to be used to help predict weather more accurately than before. During the war, we had actually had some radar operators who heard static and saw different little formations that actually turned out to be rain and other weather events. So it just made sense. Further developments are going to come about, including Doppler radar, which sends a signal out more frequently that is going to be able to actually determine movement of some of these as well. You might be familiar with this from your local weather channels, as these various measures of prediction are going to help save lives when it comes to hurricanes, typhoons, tornadoes, other formations. Also, it still is used in aircraft. You're going to say anytime you take a trip across the country or even just down the coast on an aircraft, that aircraft's going to be equipped with radar, as is the air traffic controller on the ground, who's going to make sure that your plane lands safely and at the right area. So if you've ever been on a cruise, they should be outfitted with one as well. And then many fishermen still try to use such things, smaller radar units themselves. Law enforcement uses a form of radar, even a radar gun in baseball, which is a slightly different style. It sends out kind of a wavelength that will increase in frequency as the ball approaches and gets closer, and it's going to help you read speeds. Radar has a lot of effect on your everyday life. There's a counter technology, and especially in military technology. So we start seeing development of such things as stealth fighters, stealth bombers, and stealth ships, which use special construction materials, angles, as well as electronic countermeasures And your mission today was to learn a little bit about radar. So here are a few questions to help see how you did. Firstly, what is the name of the ship where the XAF radar was tested? What did the admiral who was involved in those tests, what did he suggest? What other objects other than ships? Give me 3 uses of radar today. And then the final question is, just name 3 random facts that you learned today. Don't worry, we're not going to check your answers. This is more to see, self-evaluate, to see how you did, how much attention you paid. It's important to take each and every one of these lessons and think about, what did I just spend my time on? How did this come about? And where are we going? Come here to the National Museum of the United States Navy, check out some of the artifacts that I showed you here and then some, ask a staff member questions, read all about the different developments in history, and be sure to join us for more STEAM Saturdays. You can find at our website, history.navy.mil, and maybe inspire you to create something of your own in the future.